even if you go to this, okay, yeah, we'll share a link, and so that if you want to test, you just take maybe 1 or 2 modules, right? So within a timed period, so that you just, I mean, whatever bug you discover, and I mean, there are some metrics you need to check. So once we share that link, if you're interested in doing that, just drop your name and we'll be in touch. So secondly, the paid course we've been doing is progressing smoothly, and it's been very fantastic. People have been on my neck, as per when, in fact, they wanted to join this in the middle, and I told them that we cannot do that, simply because of the quality of what we are targeting. So we're going to start, I mean, at least the collation probably this week. We'll start the collation of, we'll start preparing for the next round, right? So that will take place maybe in the 3rd or 4th week of this month. So we'll start getting the names and registration, everything. So the information also will be dropped in the group. Okay. So that's the information I wanted to pass across. Okay, so we can start now. So alarms and safety basics. I mean, this content is not a lot, but it's very important. In the plant environment, alarms helps to keep us safe. When we say safety basics, we're actually talking about process safety, not human safety, not HSE. In the plants, there are 2 types. So we have the HSE, health, safety, and environment. And then there is the process safety, right? Or functional safety. So alarms is what informs us that the process is going towards unacceptable direction. So that's what the alarm does. So a process alarm tells an operator something is wrong, act now. Without alarms, abnormal conditions silently worsen until equipment fails, product is lost, or in the extreme cases, personnel are harmed. Alarm systems are governed by ISA 18.2. That's the international standard for process alarm management. And that's so that's the standard, ISA 18.2. All right. And the hierarchy. So we have the advisory alarms, where we talk about high, low. What does this mean? So if we have, let's say, a tank filling operation, and if we have a tank filling operation, and we're supposed to fill that tank, let's say the maximum, of course, the maximum is 100%, from 0 to 100%, right? But if it goes over 100%, there will be spillage, right? And let's assume that the fluid we are filling that tank with is combustible fluid, let's say petroleum. So the function of an alarm, I mean, the operator or the process engineer will set a limit. You can say that, okay, I want to know when the level in this alarm gets to maybe 20%, so that will constitute the low alarm. right? And then when it gets to 80% or even 70%, and that will be the high alarm, meaning that between 20 and 70%, that is what we regard as the normal operations. There will be no alarm indication, right? So that's the time we use HI and LO, high alarm and low alarm. And when process near limits, monitor and investigate, right? That's the operator action. I mean, once it gets to that limit, you check it, everything is still okay, But warning, you have HH and LL, that is II or low. That is to say, the process is at critical limits. Intervene immediately, right? Intervene immediately. So, like the example I gave, at 70%, it's high alarm. You can now set another alarm for maybe 80 or 85%, so that when the level continues to increase, 70%, you have been warned, okay, this thing is increasing. But once it gets to 85, it has become critical, meaning that what you have done here, your monitoring and investigation has not you investigated why, excuse me, why the liquid or the level kept rising, right? And then you were not able to, do anything. That's why it rose again and it got to that II alarm, right? So you need to intervene at that time, whether you implement a shutdown or you divert the fluid into a particular place or whatever. The next one is a trip or shutdown, and the term is trip. So that is the safety system threshold, and that implements an automatic action, right? It's automatically, so your trip could be set a bit higher than II alarm, right? And then initiate the automatic shutdown. So, okay, I equals to I advisory, II emergency. So the tank level at 75%, tank level at 90%, that is imminent overflow, right? Low is low advisory, and then low emergency. Okay. So the next one is permissive. A permissive is a precondition that must be satisfied before an action is allowed. That is what a permissive is. So, example, the cooling water pump can only start if the bearing temperature sensor reads less than 50 degrees Celsius. Permissive prevents equipment from starting in unsafe conditions. They are checked before the start command is executed. In control systems diagram, permissive appear as AND gates before actual commands. Let's try to unpack this. So permissives are set of conditions that must be met before an equipment starts, and it helps to prevent the equipment from starting in an unsafe condition. So the closest example I can use, we don't have permissive in in our generators, the normal petrol generators. Okay, I can't think of an example to use. Okay, yeah, let me use this. Let me use this. Let me use this. Okay, can you see my screen?
Yes, sir.
Okay, great. So now, this is a PLC block, right? A scenario for a compressor, right? Of course, a compressor is a rotating equipment, right? So, hello, please, please can you mute?
Are you sure?
Hello, please mute. Thank you. All right. So, if you look at the first rung of this ladder, can you still hear me?
Yes, sir. We can
Yes.
still hear you.
Okay,
Yes, sir.
great. Great. Thank you. So if you look at the first rung of this ladder, this is the first line that will be scanned, right? And then you can see this is oil underscore OK, temp underscore OK, vibration underscore OK. This line is implementing permissive. The permissives, right? So that is rung 001. All three must be true so that you can have a perm OK. That is permissive is OK. Right? All of these three must be true for it to be okay. If it is not true, this compressor will never start. Those are the conditions that must occur for the permissive to work. For the compressor to start. Right? So now, in this instant, if I run this program, right, the ideal thing is that this green there should be connectivity on this rung. If this rung does not work, then all the other logic under it would never work. Right? So if I come here and I start, right? If I start, if you look at this rung 004, you see that the compressor attempt to start, and look at what stopped it. This palm OK. Because this is still false. It is not true, right? The compressor couldn't start. Can you see that?
Yes.
Okay. So now let's troubleshoot this. This is the watch table. This is the watch table. From the watch table, what do you think is wrong? Look at these indicators here, right? The oil pressure is 0. The temperature is 1, is on. The vibration is on. So meaning that for this compressor, the oil pressure is not okay, but the temperature is okay and the vibration is okay, right? If you look at the watch table, you can see that the oil okay is false. So if you implement your AND logic on oil okay, temp okay, vibe okay, it is going to return false because you are having true and false. So perm okay is false. So that's why if you start the compressor on rung 4, you see that your start PB is on, your stop PB is on, but your perm okay is the one breaking the link. Are you following?
Yes, sir.
All right. So if we go to the watch table and we force these inputs, we force it to be on. So you can see what happened. Once oil okay, we forced it, and then the wrong became true. The permissive became true. You can do this normally on a physical PLC. You can force inputs, right?
Yes, sir.
Okay, great. So if you force the inputs, you force it, and then this is true, and then you can click your start, and then you see your compressor is running. So that is a function of the permissives. And I'll use this opportunity again to tell you that permissives are the first thing you check in your program. So most of the time, it comes at the very top because that is a condition that must be met. Excuse me. That is a condition that must be met for your program to function or for your equipment to function. Right?
Yes, sir.
Okay, great. So if anything happens as a function, as a system is running, right? If anything happens, like maybe the temperature went up abnormally, it's going to trip the compressor. So okay, I didn't. So when I forced this temperature to become false, right? There is a trip, right? Okay, cool. Let's get back. Okay, so that's the permissives. So you need to take note the difference between permissives and interlocks, right? So let's explain interlock now. An interlock is an automatic action that is triggered when a condition is met. The interlock reacts without operator input. The speed of response is the reason they are built into the safety instrumented system or the DCS logic. So the difference between the permissive and the interlock. So, okay, interlock, right? When you tie some conditions together, if certain conditions are met, you trigger the interlock, right? So prevent action, start blocked. It forces action. If a condition is met, something occurs, right? For example, a valve closes. It is checked before startup, right? And this is very important for those of you learning PLC, right? In PLC programming, safety the permissives are at the top, because you need to check those conditions before you start up. So generally, the instruction for permissives comes at the top of your ladder logic program, right? And this is triggered during operation. So the interlock is looking at some parameters or some conditions. It's looking at some parameters. Once the conditions are met, preset conditions, it doesn't wait for the operator. It doesn't wait for the alarm or anything. It just triggers, boom. Right? So it is triggered during operation. The permissive requires operator to enable conditions. The interlock requires conditions to be met for override. So that is, when the event is over, the operator must enable the conditions, right? I'll quickly illustrate that now. Now, the interlock, it requires conditions to be met for override. So the conditions that cause the interlock must be met. They must return back to the normalcy as we define it in order to have an override. Let me quickly show you. Let me show that. So if I force this, right? Okay, so now the compressor is running, right? Now, if let's say vibration increases and I force this, you can see that the vibration is problematic now. Oh, okay. To light mode. That's a feedback. This is the only mode. We'll work on it. So it can be done now. It can be done now. So this is the only mode available. So we'll work on it. So that's noted. Thank you. Right. So you need to reset the fault first. So look at this now. Now we went back to, so you can see all the permissives are okay now, right? But the compressor is still not starting, right? Simply because as a result of that permissive, there is this latch. We have latched the fault. Someone needs to come and clear that fault, right? So here, if I click on fault reset, then you can now start your compressor again. Is it clear to you now? Is it clear? Give me a thumbs up if this is clear. Okay, great. Because the difference between interlocks and permissives always confuses a lot. All right. So so this requires the operator to enable condition, and this requires conditions. The physical, interlocks will clear by itself once the condition returns back to safety, to safe limits, right? Okay. So we have latched alarms and trips. A latched alarm stays active even after the triggering condition clears. This is intentional. Automatic restart after trip could cause a second failure before the root cause is investigated. So you can see the reason for that latch information in the PLC program, right? So the reset procedure for a latched trip, you diagnose and clear the root cause, right? You acknowledge the alarm. So the operator confirms they are aware. You reset the latch. Operator explicitly release the trip, and then you verify conditions are safe before restarting. Skipping any step defeats the purpose of the safety system. But most of the time, you are not able to even skip it because we have hard-coded this into the PLC logic. So the ISA 18.2 principles, there are 4 different types of alarms, right? There are the actionable alarms, there are the rationalized alarms, priority limited, and then configured. So every alarm must have a defined operator response. If the operator doesn't know what to do, the alarm shouldn't exist. So for every alarm, there should be a corresponding action for the operator to do. Only critical deviations that require operator action should generate alarms. Informational messages are not alarms. Because in the plant, sometimes alarms could be a lot. And in fact, there is actually a research. If you look at this standard very well, there is a maximum number of alarms that is allowed to occur within a limit. I mean, based on design and engineering, because they realize that there is so much response that the operator can give in the face of, if you have what we call it alarm flooding. When alarm starts coming in, at some point the operator will get how will I put it now? The operator will get overwhelmed. Right. So informational messages are not alarms. Right. So only critical deviations from the process that requires operator action should generate alarms. In a major offset, less than 10 alarms. Okay, yeah. So less than 10 alarms per 10 minutes is a target. So that's a design issue. When you are doing the design of your process, right, you do it such that the operator will not be faced with more than 10 alarms within a 10 minutes range. Otherwise, if it's over 10, the operator becomes overwhelmed. And if there are alarms and the operator cannot respond to the alarms, then the alarm will likely degenerate to II alarm, and then the process will trip. Process trip costs money. They are very expensive, very, very expensive, because restarting a process, is a whole lot of thing to deal with. So more than 10 alarms per minute is an alarm flood, right? Configured, not defaulted. Alarm set points must be calculated from process limits. They must not be set arbitrarily. So the alarm set points must be configured based on the process limits. For example, for a tank, for a tank that stores gas, right? If you want to set your alarm, you need to consider the capacity of that tank. So when you have such tank, we specify them at what we call maximum actual working pressure. So they have a working pressure, and then there is a there is a working pressure, and then there is a maximum actual working pressure. You don't want to increase pressure inside that tank to such an extent that the tank will explode. Because if the pressure becomes greater than it can take, it explodes. Right? So the alarm must be calculated carefully based on the process limits. So safety layers. Modern plants use layers of protection methodology. I'll need to, okay. So there is a normal operation where you have your DCS control, and then you have your operator alarm, you have your safety instrumented system, you have your pressure relief, you have your physical containment bundle. Each layer is independent. Failure of one layer should not disable another. I will go online, I will look for a diagram to illustrate this. Right. So we have alarms, I mean, in the refinery, for example, in power plants, in NLNG, even in manufacturing, right? We have all of those alarms operational there. Okay, let me quickly check something here. Let's look at this. Very simple. All right. So this is layer of protection. All right. You can see where it is green. As the process is functioning within this layer, right, you can see the graph there, right? You can see the graph there. That is a process control layer. And that is where everything is working fine. Everything is green, good to go, right? Once this process begins to stray to the edge of this green layer, then you have the process alarm will become active to warn you that your parameters are going outside the defined limits, right? And then if it goes from here, and gets into this area, so it will have passed your normal process alarm. It gets into here, you have your process control layer, right? And then this is the limit where trip alarm occurs. Then after the trip alarms, you get into the safety layer, emergency shutdown. So you can see how it is categorized here. There is a prevention, and then there is a mitigate. So when you cannot prevent that bad incident happening, the next step will be to mitigate. So for example, after emergency shutdown, if emergency shutdown still did not bring the process to safety limits without incidents, then let's assume that fire breaks out here, or there is a spillage and all of those things. Then you now have your mitigation actions, where you have your active protection layer. Active protection layer, things like pressure relief valves, your PRVs and your PSVs, and then passive protection layers. So you have your dike and your bond wall. So for example, in petroleum storage tanks, you will see that they built a wall around it. That wall and the size and the volume, I mean, it wasn't built arbitrarily, it was calculated. It was calculated to be that the content of that tank, if it spills, it will be contained inside that bond wall so that it won't flow, you know. And then, God forbid, if everything fails, then emergency response, evacuation, and all of those things, of course. So that is, we call this the LOPA, layer of protection analysis, right? Where we identify the different layers of protection for the process. So it's represented in different, so this one is showing so you can see this one now, the process, you can see, so everything is enclosed. So this is the basic process control system. Your DCS normally is the basic process control system. Then outside it, you have your instrumented SIS, safety instrumented system. All right. And then you see the hierarchy over there. Okay. So I wanted to show that. Excuse me. Okay. So, I mean, the walkthrough, we'll go into the simulation now all the time. So if I say it's okay, making good time. Anyway, this is not much really. So the initial step one, normal operation, initial state 40%, inflow 35%, outflow 35%, right? So that will maintain this level at 40% because inflow equals to outflow, right? So the level controller is maintaining the tank at its 50% set point. No alarms are active. Observe the alarm panel, all lights are green. The permissive is on. That is, the pump is allowed to run. Key concept, in steady state, inflow is approximately equal to the outflow. The controller makes small adjustments to maintain balance. This is the state the operator aims to keep the plant in. So tank level is simplified to a linear model. Real tanks also exhibit gravity head effect that slightly changes outflow as level rises. The alarm logic and response principles are identical regardless. So that's step one, normal operation. Step two, high alarm at 75%. Increase the flow slider to 70%. Watch the level rise past 50%, which is a set point, through 60 and then cross the 75% mark. When level is greater than 75%, the high alarm fires. The alarm panel shows a yellow eye indicator, high alarm indicator.
Sorry, I can't see your screen.
You said? You said
I
what?
can't see your screen. Yes, screen. The share screen. You can't see it.
Is there everybody that can see my screen?
We can see it. You should probably
Some of us
rejoin.
can see.
I can see it.
Okay, so quickly, I'll just give like a minute. Quickly log off and log back in. Must be from your end.
Okay.
So quickly log off and log back in. We'll still remain on this before we go to the simulation. So the operator, okay, so that's the high alarm. I mean, that's the process we'll go through. right? Operator action. An operator will reduce inflow or investigate the root cause. In this simulation, increase the outflow slider to counteract. Note, the I alarm is advisory, so there will be no automatic action, right? The process can continue safely while the operator investigates. The I alarm is just to inform the operator that, hey, the process is approaching the II alarm, which can lead to a process trip, right? Then the II trip, keep inflow at 70% and reduce outflow. Watch the level continue rising. When level is greater than 90%, the II set point, the safety trip activates. Inflow valve automatically closes. The HH alarm appears red and lashed on the alarm panel, and then the pump permissive drops out. So that is, at that point, the pump is not allowed to run. The level stops rising because the inflow is shut off. Outflow continues to drain the tank. So the concept here is that the trip acted automatically. No operator action is required. The latch remains active even as the level drops below 90%. So and that's what I illustrated on that PLC scenario. And then step 4, the reset procedure. The tank level is now dropping. Outflow is greater than inflow. Then the HH latch is still active, even though the condition has gone below the HH, right? So the step 1 is you confirm that the reason for this is cleared. Step 2, you confirm that inflow is now controlled. You acknowledge the alarm. You reset the latch. Once you reset the latch, that is only when the pump can now be restarted. Right? So, and you should do this only when you have cleared the root cause, because you don't want it repeating again. This is not like the phone that is faulty and you just restart. In process control, we want to understand what caused that II alarm or what caused that trip. So we'll do that investigation, then we'll reset. All right. So can you see my screen now? The person that said he couldn't see the screen earlier.
Yeah, just go on. I think maybe there's issue from my own end.
Oh, okay.
Okay. Thank you.
Welcome. Okay. So this is a normal operation. So let me talk about this. So this is the controls. This is the alarm panel. The I alarm is set at 75. The II is set at 90%, right? The level at 40%. This is the slider to increase or reduce the inflow, and this is for the outflow. So you picture a tank that has an inflow and then has an outflow, right? Now, as you picture that now, begin to look at the kind of controls that is attached to such a tank. You need to control the inflow. You need to control the outflow, right? And these are the things when you want to write your PLC program. These are the considerations. I mean, this constitutes part of your planning. So the question is, what is controlling the inflow? Maybe there is a control valve there, right? That you are opening or closing, and you are taking the status of that valve, you are wiring it into the input card of your PLC, right? And then at the outflow also, there is another valve that you can use to open and close within the range of 0 to 100%, so that if you want to increase the rate of outflow or reduce it or totally shut it off, that needs to be there. And you wire that valve also to your PLC. Are you following? Am I making sense? Okay, great. Thank you.
Yes,
Right,
sir.
you wire that also into your PLC, and then okay, and then the level inside your tank also, you want to monitor it, so you implement a level transmitter, and you wire that also into the input of your PLC. And then in your PLC, you now configure your alarm limits. You configure your low alarm, your low alarm, your high alarm, your high alarm. So let me ask you a question at this point. How does your PLC knows when to trigger an alarm? What tells the PLC is not present on the tank, it's far from it. So what tells you that, hey, this condition has been met, so just give an alarm? Do you understand the question?
The on-field equipment such as the level transmitter, throw transmitter, and sorts.
Okay, yeah, you're right. So the sensor or the level transmitter, that is what. So the controller is continuously reading the level, right? You implemented a level transmitter in that tank. So the controller is currently constantly reading the level, and the level is the PLC will look at the level, compare it to what you have set as your high, low, and then indicate accordingly. So you can see that flow. So if this is a closed tank, for example, as you have implemented a level measurement in that tank, you probably want to implement a pressure measurement also, so that you can keep an eye on the pressure inside the vessel. So you can keep an eye on the pressure inside the vessel, and maybe you want to keep an eye on the so we've measured level, we've measured pressure. You can keep eye on the temperature depending on the fluid also. You can keep an eye on the temperature both inside and outside the tank, so that if temperature is critical, if, for example, you have an equipment that has, a process fluid or a fluid that is sensitive to temperature, that has a very low ignition point, you want to be sure that the temperature in the environment of that fluid is, way below the ignition point of the fluid itself, right? So you can begin to see how instrumentation quickly escalates. The inflow into the tank, there is a pipeline there. There are some monitoring and control you want to implement on the pipeline, not just on the valve. You can implement flow, right? You want to know the flow rate, the rate of flow into the tank. So you can implement that. On the outlet also, you can implement flow. Are you following?
Yes, sir. Yes, sir.
Okay. Yeah. So let me see one example. Let me quickly show one example. Uh, okay, so this is a proper process, right? This is one vessel. Can you see my screen?
Yes, sir.
Okay, so this is a proper process, right? This is a vessel. This is a very popular operation in the oil and gas environment, right? You have this is called a separator. When the crude oil comes in, right? The crude oil comes as a mixture of water, oil, gas, and even sometimes sand, because it's coming from the earth crust. So it carries sand, then mixed with water, with oil and gas. We are only interested in the oil and gas. I mean, the water, we have enough water, right? So we want to find a way to separate these components, right? We want to separate the water and purify it and return it back to the environment. We want to separate the oil and then pass it into a storage tank or further treat it or pass it to a refinery. We want to separate the gas because gas needs to be handled with care rather, right? We want to separate it so that we can either send it to the flare and burn it off, or send it to a compressor station, perform further processing on it. So everything comes in as one inflow, and then we have 3 outlets from this one tank. That 3 outlets, we must take care of water, of oil, and of gas. When you begin to look at the different processes on this tank, so these are the controllers we have now, right? You have the level, so you are monitoring level. So you have LIC 201, you have LIC 202, right? So that's the PV, the SP, the OP. You have your PIC 201, right? You have your ESD, right? So, okay, yeah. So these are the process values. Okay, no active alarm. I mean, so this is mimicking the HMI. So all the alarms, once you begin to run your operation, all the alarms will be active here, right? So you have your active alarms, you have your event log, you have your I alarm level, pressure, oil pressure, and then this is the gas pressure, and so on and so forth. So the threshold for this one is 75, the threshold for this is 1,100, and the direction is above. So you can see how all of those are defined, right? Let's see. Okay, anyway, let's so the point I'm trying to make is, when you look at a tank, you don't look at it in isolation. The tank is connected to an upstream process. So this upstream process is so somewhere here will be the oil well, what you call the Christmas tree, right? The Christmas tree, or the wellhead, right? So it is the wellhead that is feeding this particular pipe, and you have this inlet valve. You can see the capacity of that valve, right? Then that's it's a XV, it's a block valve, and it is opened. So it's dumping everything in this tank, and then this tank, using mechanical principles to separate all of this, and then separating the output. So you can see how the process works. Okay, so let's get into this. Yeah. So let's start. Okay, let me just use 2x so that we can see. So you can see the process. So the level is at 40%, right? The set point is 50%, right? This line here, that is the I alarm, and that is the II alarm, and that's where your trip comes in. So you can see the I alarm is set at 75%, and the II alarm is set at 90%. So the system is working normally, the permissive is on, and everything is going smoothly, right? Let me pause. Now, the activity says increase inflow above 60% while keeping outflow at 35%. The implication of that is that the tank will now be going towards overfilling. There will likely be a trip if there is no intervention, because we are taking the inflow to go above 60%. So let's say 64%, and then the outflow is kept at 35%. All right. Then let's resume. So you can see the level rising. It's rising above the set point. All right. Rising above the set point. You can see it keeps going. It stopped. Let's stop it. We'll reset. Okay. So you can see the I alarm. The I alarm kicked in, right? And then you can see the II trip active. So immediately the II trip, you can see that the level started going down. So the job of that trip is to bring that process back to a safe condition. So the II trip active blocked the inflow, right? So it blocked the inflow, but the outflow was still active. So you can see that this II trip has been lashed. So it needs to be cleared before the operation, right? Okay. Okay. So continue increasing inflow or leave it high until level 90. So we've achieved that. All right. So I have a question here. Why are HH trips lashed? The HH trip remained active even after the level dropped below 90%. What is the engineering reason for this? So tell me. To generate more alarm notifications for the operator, to prevent the process from restarting automatically before the operator checks, to keep the plant running at reduced capacity after the trip, to permanently disable the tripped equipment until maintenance replaces it. Tell me, what's the answer?
Is B.
D.
So the
answer is
D.
B.
B.
B,
Yes.
B.
Okay, right. So
You are meant to clear the alarm before you restart the equipment.
correct. So that's it. So now complete each step in order. level drops below 75, auto check after trip drains. And step 2, inflow slider to greater than 20%. That is control restart, right? So if you reset, right, clear and whatever, so you bring your inflow slider, you start your process gradually. So you put that, your permissive is on, right? Your permissive is on, and then you start gradually, right? So, oh, okay, I shouldn't have done the reset. Okay, let me do this. Oops. Let me quickly go back to that condition. So if we reset, okay, let me go back. Let me go back to this, less than this. Okay, I'll need to reset to, okay, reset. So it's less than 20. Then, so that's a bug in that simulation. We should be able to continue from the level we were in, after the trip. Okay. So, what's the level 0? Okay. So why is the level 0? Can you tell me? Because we set our inflow at 19.
Yeah,
Why is the level 0?
flow.
Huh?
And the rate at which it is outflowing is more than the rate at which we have an inflow.
Okay, you called that. Exactly. So inflow is 19, outflow is 35. So yeah, correct. So if we want anything in there, let's okay, no, I'm not continuing. Let's start. All right. Let me see what is happening. Let me just see where it's going to stop, because the inflow. Okay. Okay, you can see what is happening there, right? The I alarm occurs also. The rate of outflow is very low. So the liquid is accumulating. So at this point, if I intervene because of this I alarm, right? So I increase the rate of flow and just a little differential, you can see the response here. So start dropping. And if I really want to bring it within control, okay, it just stopped. So, but that is clear to you, right? The conditions that brings the I alarm and the II trip, right? So let's get into the quiz and see. So 1 of 9. So you can just tell me the answer. What is the main purpose of the I alarm? A, to immediately stop the process. B, to warn the operator. C, to increase production. D, to disable the sensor.
That should be
B. No wonder
B.
operator.
To warn the operator. Correct. Right. What is the main purpose of a II alarm? II trip or shutdown? To make the process faster, to protect equipment, people by forcing a safe state, to improve sensor accuracy, to reduce set points permanently.
That's also
B.
Yeah. Okay. A permissive is best defined as
yeah, that's B.
B.
Yeah.
Yeah, B.
So it's not manual override. We have something called manual override in the plant, right? Where the operator takes control of the process. So even though the process is saying this, then the operator steps in. So that is not, that is not the permissive, right? So an interlock is best described as
The answer is B.
is B, a system that posts trends and automatic action that forces a safe condition, right? Alarms and trips exist to improve safety and protect equipment, even if they reduce production sometimes.
True.
That's true.
True or false?
True.
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 Okay. In the tank level simulation, when HH level trip occurs, the correct protective action is open inlet valve wider, close inlet valve trip, increase set point, disable alarm panel.
Close inlet valve.
Closing net valve.
Right. Which steps are commonly required to recover from latched trip? Select all that apply. So tell me, should I select A?
I think the first step there is to acknowledge the trip alarm.
You said?
I think the first step is to acknowledge the trip alarm.
Okay.
B, then A.
Then
D. D.
A, B, D.
So, okay. So A, B,
B
and
and
D. Okay. So latch trips require condition cleared plus acknowledgement plus research/permissive re-enable before start. Right. A tank level is rising. The I alarm fires at 75%, but the operator ignores it. The II trip fires at 90% and shuts the inflow valve. What was the operator's critical error?
And the operator failed to act on the advisory guideline.
Yeah, so the operator failed to act on the advisory I alarm before the emergency condition developed. So the II alarm, the alarm escalated. So after a II trip shuts the inflow valve and the tank level drops back to 65%, the operator resets the II latch and immediately reopens the inflow valve to full. What happens?
the process should trip again. It should be press the chip again.
Any other opinion? I see another bug. All the answers we've been saying B.
Well, except
So-
the true and false question.
Yeah, I said it for false. Whatever. I've noted it. Okay, someone Abubakar said A. So what's the answer to this? After I trip short the inflow valve and the tank level drops back to 65%. Okay, another person says B. The operator resets the II latch and immediately reopens the inflow valve to full. What happens? The system resumes normal operation. The process trips again immediately. The root cause was not clear. The I alarm fires, but not at each trip. The latch prevents the valve. So B, right?
Yes.
Yes, sir.
Okay. That quiz is too cheap. You know, in Nigerian universities, you can't. It's a sacrilege for you to be getting 100%. Yeah, you are proving over Sabi.
It's also a credit. It's a credit to you also for better explanation.
Is it?
Exactly.
No. It shows that you are doing over Sabi. I can't even be scoring 100%. Okay. All right. What's the time? What's the time now? This is 8:23. I think we're at the limit of our time. So, let's see. I'm thinking, fundamentals. The next class, this is just applied control. It's a case study. So probably we'll start another series. I'm thinking we'll focus on the PLC next, but we'll announce it. We'll announce it. So, any question so far?
Yes, sir. Can you please go back to question 8 in that quiz?
Sorry, say that again.
Can you please go back to question 8 in the quiz, sir?
Okay. So I have to run through it. So anyway. Oh, okay. Okay, this question 8.
Yes, sir. I think when we did this, you said the answer is B. But
Yeah.
also, would A also have been? I'm sorry. Would A also would have been a good correction or the critical error the operator made?
Okay, let's look at the question again. A tank level is rising. The I alarm fires at 75%, but the operator ignores it. Remember, the I alarm is like a warning. Now, the II alarm fires at 90% and shuts down the inflow valve. What was the operator's critical error? So in this instance, A says the operator should have manually increased the outflow before the II trip. Okay. So if the operator increases the increase the outflow, so using that slider now, right? If he increases it, then the process might not get to the 90%. Yeah, it's a possible answer.
All right, thank you very much. I was also considering that earlier.
Yeah, it's a possible answer. So again, so there are two possible. Okay, what was the operator's the critical error? The operator failed. So the operator failed to act on the advisory alarm before the emergency condition developed. The operator should have acknowledged the I alarm. The operator should have reset the latch immediately. Definitely not D, not C. So now, again, let's look at it. A is a possibility to prevent the II alarm, right? But the trip already occurred, and the question is asking, what was the critical error? So this is a look back on what has happened.
Oh, I get it now.
Yeah, so it's a look back on what has happened. The reason we had that shutdown is that this operator failed to act on the advisory I alarm. The action the operator should have taken is to implement A. If he had implemented A, if he had implemented this action, then the trip would not occur. So this is an investigation on what led to the trip. So B is actually the right answer.
Well noted. Thank you, sir.
Okay, cool. So I'm just right.
So I have
Okay.
a question.
Okay, tell me.
The question 7, you mentioned that the permissive must also be reset, but on that simulation you did, when the fault came up, the permissive did not go off.
Yeah, I noted that also. I noted that. So I've noted it. I mean, so that's why I'm using this platform. You know, we still have bugs here and there.
Right.
So that will be corrected. All right. So any other question? Caleb raised his hand the other time.
Well, I already asked that. It was me.
Okay, cool. Okay, so looks like we're all good. So we can get on with the weekend. So enjoy your weekend. Okay, Abdulatif.
Yes, sir. Regarding the question 8,
Yeah.
where you were analyzing the option or the A option.
Yeah.
Is there ever a situation where there is like a flow sensitive process where if for whatever reason there's a manual alteration to the flow, there will be a problem in the process. Are there flow sensitive processes like that? Because I'm thinking if there's a flow sensitive process like that and the operator manually alters the flow rate, there will be a problem. Is there a real time flow sensitive processes?
Yeah. So the system configuration. I mean, you know, humans created the system. We designed the system, right? We have looked at all the possible scenarios and provided safeguards and operational guidelines, right? But generally, when you are operating, you have your auto. You can operate in auto and you can operate in manual, right? So for that, if auto is not giving the results the operator wants, or for some reason you can achieve. So when you are in auto, you are using the PV from the process, the SP from the, okay, let me run this now. Right. So you are using the PV from the process, the set point, right? And whatever, so you can change from auto to manual, right? So that you can now manually alter this. Why is this, this OP? What's OP now? That's your output. So you can manually alter this, right? So that you can manually open valve or close the valve for whatever rate you want it. So to answer your question, the system is on auto. The operator can manually intervene, and that's why the operator is there. I don't know if I've answered that satisfactorily. Okay. All right. All right then. Thank you. Okay, guys. So let's have a very wonderful weekend. Thank you for your time.
Thank you so much. Thank you for coming.
Thank you, sir.
Thank you, sir. Thank you.
Yeah.
Thank you,
Bye.
Master. Thanks, bye.